So it's my pleasure to reintroduce May,
Take
who
two.
hopefully is working sides. So
Yeah,
people know. Great. Okay.
I'll
Sure.
just
Fire ahead
jump.
there, Maeve.
I'll I'll go straight into it and see if this works now. Full screen. Okay. I don't know if that's working today. It's one of those days this morning, so I might just leave it on this screen if people, if that's okay. I don't want to mess around with it because it's already kicked me out once today. So hello everybody. So today I'm going to give you a brief insight into work that I did during my PhD with Professor Andrew Parnell and Dr. Niamh Cahill-Maynooth. So we were looking at Bayesian generalized additive models for quantifying sea level change. And this work was part of a big group called the A4 project. So we worked with lots of geologists, oceanographers, looking at very different aspects of climate in the North Atlantic. So to start, this is just a structure for the talk today. I'm just going to give you an introduction in relative sea level change, the data that we used, the noisy input generalized additive model for looking at this relative sea level change, a slight kind of look at the OR package that we developed with the techniques that we talked about, and then some potential future work. So that's what I'm going to start with, is what is relative sea level change? And I think we all have heard so much on the media about climate change and rising sea levels, especially in Ireland, where we have 40% of our population is within 5 kilometers of the coast. So these kind of challenges for today, I'm going to focus on the North America Atlantic coastline, but it's similar kind of processes can be applied to Ireland and further afield. So starting with what is relative sea level, it's the difference between the sea surface level and the Earth's sediment surface, and it's a complex pattern of interactions that vary in time and space. So with relative sea level, there's lots of different drivers that can impact it both in space and in time. We've 4 examples that I'm going to talk through today. So you have your melting ice sheets. If you melt a glacier, you're distributing more fresh water into your oceans. Then you have warming oceans. If you heat a body of water, it expands, hence our sea levels will rise. GIA, or glacial isostatic adjustment, this is kind of a physical phenomenon that results from if you have a glacier lying on a plate, it causes your plate to deform, and somewhere else it has to uplift to compensate. So relative sea level and GIA is very important because we had massive ice sheets and we're still feeling the effects of them today. So when we look at the data, you'll see that the data goes back 3,000 years. So this kind of physical phenomena is very important. And the final factor are local factors. This is site specific. These could be changes in sedimentation, changes in tidal dynamics, and they all give rise to relative sea level change. So the data, so what type of data do we use? We go out to the field and collect proxy data. So we have a combination of 3 options. You can either use satellites, which are really accurate and they're very good, but they only go back 25 years roughly. So we tend to not use satellite data. It's kind of one of the future works, but it's at the moment it's not useful enough for us. So we focus on tide gauge data. So tide gauges, you may see them along your coastlines. They monitor tides, and there's a global tide gauge network that has about 80 stations, and that's looking about 150 years. And then the final one, and the one we focus on, are proxies. So proxy records come from salt marshes, and you can use them to identify how sea level varied over long-term changes for 500 years, all the way back to, let's say, the last glacial maximum. So what sites that I'm going to show you today, and it's kind of coming from the paper that we wrote about this, is we have, I think it's 67 tide gauges and 20 proxy sites. Today I'm only going to highlight results from 4, but I just wanted to make sure that the model is run using all this data, and it's given us insights in how it's changed along this coastline. So for today, we have 4 proxy sites that we're going to focus on. And you can straight away see that we have these black dots and then we have these grey boxes. So these grey boxes represents the measurement uncertainty that we obtain when we go and collect these proxy records. So proxy records is not a very straightforward technique. When you go out to your field, you take a core and you take samples of how the sea level changed with depth, and then you use statistical models to get relationship with depth and sea level. And then we also do dating, carbon dating, which then all links together to give these final results. There's a whole another section to how the data is processed, but I'm only going to focus on the final product. So you can see how the 4 sites vary differently in space, and the size of the uncertainties also vary hugely. For example, Swan Key in Florida has these huge uncertainty intervals because of the type of material that they were collecting the data from. So these are things that we have to incorporate in all our models, and it makes for interesting statistics, but also a few challenges as well. So the approach that I'm going to talk about today is the noisy input generalized additive model. And essentially we have kind of 3 prongs that we focus on. We have the Bayesian hierarchical framework, we have our generalized additive models, and then we have a noisy input uncertainty method. So as we've all talked about today, with our Bayesian framework, we have prior information and the likelihood to estimate these unknown parameters. The priors are very useful for us because we have lots of information from physical models that we can incorporate into our priors. But there's also challenges with, let's say, sampling. We use JAGs to do MCMC sampling. It's probably more efficient methods might be in the future works, but this is what we've used for now. Then at a process level, we use generalized additive models. Essentially, we're using like a sum of different splines. Splines are very useful. They're very flexible and extendable. So we have these kind of like little basis functions that we penalize whether we want to make them or weight them, whether you want them to be bigger or smaller. You can have many different types of basis functions, and you can kind of use different ways to ensure smoothness across different locations or in time. So we did lots of different kind of tests on which one was the best one, and I'm just going to show you the results for that one in a little bit later on. Okay, so the last component is the noisy input uncertainty method. As I showed you at the start, we have these large uncertainties in both the input and the output. So there's this technique that Matt Hutchins and Rasmussen developed in using Gaussian processes. We've kind of adapted it for GAMs instead. So essentially you run the model 2 times. So you start off with no input noise, and then what you can do is you calculate a corrective variance term. This is essentially the derivative of the posterior mean at each data point. And then you rerun this model with this extra corrective term in the variance structure. And this allows you to like overcome these inputs by inflating the output variance. It's very useful because the 2-step modeling process lets us do kind of learning of informed priors. There's lots of different advantages from running the model twice. And it helps us kind of get over kind of identifiability issues that we had with the different components. So let's just give a brief summary of what I've talked about for the Bayesian hierarchical setup. We have this model run 1, which is using your proxy records and your tie gauges with this associated uncertainty in the response. So you have your sigma y, which is your model residuals, and then you have your sy, which is the observed uncertainty that we had with relative sea level. Then we rerun the model after calculating this corrective variance term, and then we are able to incorporate the unknown uncertainties for our observations in time. So that would be our data level. At our process level, we have a spatial temporal relative sea level field. It's formed by like a sum of random effects and spline functions. And the idea is that we're going to try and capture these different drivers of relative sea level change. It's inspired by work by Koppen over in the US, and we've tried to adapt it and make it more efficient in this example. So to just do a quick recap, we have our 4 main drivers, and we'd love if we could separate out our model to identify where or when these kind of components of relative sea level are most important or most influential. So the idea is we're going to separate them out into a regional component, a linear local component, and a non-linear local component. And then we're going to apply some sort of spline in time. a random effect term for the linear local component, and then this spatial temporal spline for a non-linear local component. So our process level for this relative sea level field is going to be these separate components. So our regional component, the idea with a regional component, we want to look at how things change over time for this whole region. So this is going to be represented by a spline in time. Then we have this linear local component. This is representing things like our GIA, which is our glacial isostatic adjustment, which is kind of assumed to be linear over these longer term timescales. So we use a very informative prior on this component to look at how these different locations rebound after the plate or the glacier melts from the plate. And then the last component is our non-linear local. This is kind of capturing what's left over, because we've worked with our geologists and they've recognized that the regional component and these GIA influences are the most influential. But at a local level, we need something to capture kind of site-specific changes. And this is why we use our spline in space and time to capture these kind of leftover bits. So our results for our GAM or NI GAM. So what this is telling us is that we have our 4 separate components. So our green is that linear local component. Our brown is this non-linear local component. Our blue is our regional component. And then our purple is kind of the total model fit. And I am including this plot to kind of give you a sense of how different components interact with each other and how they become more or less important throughout time. So essentially what we can see from Cedar Island in North Carolina, we start seeing this is kind of there's wiggles around the main fit, but this is reflective of what's happening at a local level. But you can see that it's generally linear up to about like maybe the 1800s. And what's happening here is that there's this kind of uptick happening. And this uptick is a result of regional component effects. So these effects could be your melting ice sheets, your warming oceans. And it's really evident that you can see that this kind of recent changes is something that we haven't seen before. Now, it's not as evident in places like Placentia and Newfoundland. This uptick isn't as clear, but you can see that there's something much more dramatic happening at a local level for Newfoundland. So the importance of these models is that we're able to identify these different drivers. And from a geologist's point of view, they're really interested in seeing, okay, that there's these different components, but can we get a sense of how these change by site? So we can look at this a little bit further and we can see how well this model fits for our data. So this again, our black points are the midpoint of these boxes, and these boxes represent the observed uncertainty. And you can see that sites with gaps and less data are learning from sites with more data. That Swankey has, again, I identified that these larger uncertainties results from the data collection method, and our credible intervals are inflating to capture those larger uncertainties in the data. So you can start seeing how different sites are very different, and what we would be I'm very interested in looking at is rates of change. So if we are at a specific location in Florida, you can start seeing that rates of change are hitting about 2.9 to 3 millimeters per year. And already Florida is at sea level. So these kind of rates of sea level rise are really dramatic and really scary for people who live in Florida. And that's already been observed. And different locations have different kind of rates of change. So this is highlighting to us that we have to kind of incorporate both spatial changes at different locations. Like Placentia definitely doesn't have as high a rate compared to Swankey in Florida, but these kind of incorporating the different components and also how these interact with each other are very important. Then we have this regional component. So this regional component is telling us how, on average, does sea level change across the Atlantic coast of North America. And again, we're starting to see these dramatic increases in recent years. So we can look at what these kind of wiggles mean in a sense of there was warming medieval periods, there was little ice ages, and these kind of influences can be detected in like a regional component. We can also look at the rate. Again, we can see that rates for this area is hitting about 1.7 millimeters per year for the whole Atlantic coast of North America. It's on the lower scale when you're comparing that to global rates, which is about 3 millimeters per year from the IPCC reports. But you can imagine that this is like a combination of different locations, and the resolution of our proxies are much lower than what they would use in IPCC reports from satellites. But it's very interesting to see these kind of rates are alarming. The other thing that we like to look at is like our local nonlinear components. So this is if you're in specific locations that you might have influences, maybe tidal regimes or different sedimentation rates that need to be incorporated, that results maybe in faster rates of rise, or could be like other changes in your so for example, Placentia is a very good example, because what's happening here is that there's some sort of sedimentation rate that closes and opens an inlet over long-term timescales. And you can also identify things like building works. When you use nonlinear local component, you can see when they put bridges into different locations and how that changes the tidal regimes and sediment regimes in specific locations. So these are kind of really interesting things that we get from these separate components. And from a physical point of view, these have really dramatic impacts of how you're going to plan for your future sea level rise. So that's kind of like from a very applied Bayesian approach. And we put all of this kind of into a package called Wrestler. So this package is looks at examining proxy records and tie gauge data, and it performs Bayesian modeling for different statistical approaches. So we've included a very different number of models within this package. And the idea is that the framework is very accessible, because we tend to work with a lot of different groups with different levels of coding and statistical backgrounds. So we try and have a framework that loads the data, fits the models and plots, and summarizes the results. It is available on CRAN, and there is more information on my GitHub, but just to give a sense of all the different options that we give to within the package, is that we have we have a simple linear regression if you want to just look at rates at a specific location. We have a change point model, which identifies where trends change and looks at how rates vary above and below change points. Change points are very interesting at the moment because they are used in lots of different areas, like temperature, and also in ocean dynamics. It's coming into play with tipping points. Then we use an IGP, so that's an integrated Gaussian process, which looks at specific locations. And then we have also splines, all our splines that I've talked about already today. These are just given different options to the user, depending on their type of data or depending on what they want to understand from a sea level point of view. These have all been used in the literature before, so this is why we've incorporated them in the package. But it's just it was an interesting kind of taking your statistical approach and putting it into a package for not just like statisticians, but also for different users. So that's kind of what the work that I did during my PhD. The future work, there's always future work with all of these topics. It's never ending. But the first future work that we were very interested in looking at and will be using topography to better understand sea level variation along coastlines. Something that I haven't looked at yet, but it's something that would be cool to incorporate for definitely for planning for future change. And then also looking at incorporating other physical processes. So we know that ocean dynamics plays a huge role with sea level. And I don't know if people have seen the news at the moment, but there's a lot of talk about well, I won't call it the Gulf Stream, but is the current system in the Atlantic slowing down? So we have a lovely temperate climate, thanks to lots of ocean current circulation patterns in the North Atlantic. Can we use our statistical models to identify how is this a long-term change, or have we hit this tipping point? So this is kind of future work that we'd be really interested in looking at. I am already at my summary. I've talked very fast. I feel so I will sum up. Relative sea level is the difference between sea surface level and the Earth's sediment surface. NIGAM allows for flexible modelling of different components for relative sea level while accounting for uncertainty. And the Ressler package allows for modelling of relative sea level data from proxies and tide gauges. I'd like to say it's not this idea, this approach could be applied to different areas of climate, definitely kind of temperature using proxy records and temperature. It's definitely open to lots of different areas. We haven't looked into them, but it's definitely yeah, able to do it for future work. And there is references, so we do have one paper is in the Aura journal and the other one is currently under review. So here's my references, and yeah, I'm going to leave it at that because I know you want lots of time for discussion. So thank you, and we'll hand it back to you, James.
So thanks very much for that, Maeve. So I'll open the floor to any. I think we've time for one or two questions. So I'll open the floor to anyone who has a question, and then I can follow up afterwards. Okay, so I'll step in. So I suppose I've seen a version of the talk before, so it's rather unfair because I know the questions to ask. But from I guess from a topographical perspective, so incorporating the landscape into the models, what differences do you think that will make potentially to the outputs?
I don't know if they'll have a huge change because the resolution of the proxy records are very it's not very, the data is very uncertain. So the topographical point of view would be looking at, let's say if we wanted to look at the North Atlantic, and it'd be really useful if we could incorporate the topographical with satellite data so that we'd have this high resolution data, and then we have this lower resolution data that gives the more temporal resolution. So it's kind of it would be a bigger kind of work. You'd have two sources of data with very different uncertainty values, but to incorporate the topography would be very important for looking at, let's say, global trends across an ocean. So like we've just focused on a region here, but incorporating how the ocean basin looks will be very important for that kind of sea level change at bigger scales.
Yeah, I guess, or even some of the barriers across, or the barriers, like the topographical barriers that may exist in the surface landscapes.
Yeah, definitely.
And your results were all in America, I guess. Is it possible to replicate this work in an Irish or European context?
Yeah, we've been working with, currently we're working with a group in Singapore. They've currently put together data in with different areas in Singapore. In Ireland, yeah, that was the plan. The data is currently still being tidied up. So when that data comes in, we'd be able to apply it. I don't actually know what that status is. I probably should check that. But yeah, it has been done in Ireland, and we're just waiting for results. But yeah, exciting.
Yeah, probably a typical example of PhD work data appearing about 6 years after the PhD.
Especially with the geology stuff,
Yeah,
it takes 3 to 4 years to collect data from mud to the final product. So lots of time that's gone into it.
yeah, okay, great. Just keeping an eye on the time. I think we're moving towards a general panel discussion now. So thanks very much for that, Maeve. It was very interesting.